Welcome. Today we're diving into the world of machine learning, starting with one of its most fundamental concepts, univariate linear regression. Imagine you want to predict a continuous value like the price of a house based on just one feature such as its size. That's where linear regression comes in. It's a supervised learning method that finds the best straight line to fit your data, allowing you to make predictions. We'll explore how this works, why it's useful, and set the stage for understanding more complex models. By the end of this video, you'll have a clear grasp of how linear regression forms the backbone of many machine learning applications. Let's break down how univariate linear regression actually works. The goal is to find the best fitting line through your data points, using an equation like y equals theta 0 plus theta 1x. Here, theta 0 is the intercept and theta 1 is the slope. We use training data pairs of x and y values to estimate these parameters. The difference between the predicted and actual values is measured using a cost function, often the mean squared error. By minimizing this error, we find the optimal line. This process can be done analytically, using formulas based on statistics like variance and covariance, or iteratively, using algorithms like gradient descent. Both methods aim to make our predictions as accurate as possible. Now let's talk about gradient descent, a powerful algorithm for finding the best parameters in linear regression. Imagine you're on a foggy mountain trying to reach the lowest point. Gradient descent works by taking small steps in the direction that reduces the error the most. Starting from an initial guess, it updates the parameters step by step using the slope of the cost function. The learning rate controls how big each step is. Too small and it's slow, too big and you might overshoot. This iterative process continues until the error stops decreasing significantly. Gradient descent is especially useful for large datasets or complex models where analytical solutions are impractical. See linear regression in action using Python. Libraries like NumPy and scikit-learn make it easy to implement regression models. With just a few lines of code, you can generate data, fit a model, and visualize the results. Scikit-learn, linear regression class, computes the best fitting line by minimizing the mean squared error, while SGD-regressor uses gradient descent. You can even apply these techniques to real-world datasets like California housing to predict house prices based on features such as median income. This practical approach helps you understand not just the theory, but also how to apply linear regression to solve real problems. Finally, let's look at linear regression from a statistical learning perspective. Here, we model uncertainty using probability distributions. The predicted value is not just a fixed number, but includes a random error term, often assumed to follow a normal distribution. This approach allows us to interpret predictions probabilistically and connect regression to concepts like maximum likelihood estimation and Bayesian inference. By understanding the statistical foundations, you gain deeper insight into how models handle uncertainty and make predictions. This perspective is crucial as you advance to more sophisticated machine learning techniques where probability and statistics play a central role.